We've been working with the natural number e here just recently. Remember, e is about equal to 2.72. Well, when we first learned e, I talked a little bit about where it came from. And it comes from a little manipulation of our compounding interest formula. It's been rearranged here a little bit, just using some laws of exponents and some substitution. But this quantity in here is what we talked about in terms of where e, the natural number, comes from. If you increase your compounding periods to infinity, so you don't compound it every minute, you don't compound it every second, you just continuously compound it as often as you can. So m gets really large, and this number approaches e. And so what that allows us to do is to write a new equation for continuously compounded interest, where the amount you end up with is equal to your principal, p, times e to the RT. I've got these all spelled out on this next slide here. So p is the principal. E is the natural number now, 2.72 approximately, but we'll use the value of E, which is in our calculator, or at least a close approximation is in our calculator. R is your interest rate, the annual rate they're going to give you on your money that you invest or put into the bank, written as a decimal. And T is the time in years that you're going to leave the amount in the bank. So today's assignment is just essentially to use this equation. I did want to point out, though, I did a little comparison here of money being compounded at different rates. Well, not different rates, by different methods. So in this case, the red line here, that is using the following formula. I believe it was $1,000, yeah, we started with. The rate was 10%, so it was 0.1 times t. And then for the blue, I did just compounded annually. And so that equation was exactly the same thing, except instead of e as a base, it was just 1.1 to the 0.1 times t. So this was compounded annually, and the red was continuously compounded. And it's kind of hard to see, so I'm going to zoom in here. But here I've marked on the graphs, the red and the blue one, the red being the continuously compounded, their value after 10 years. So after 10 years, your $1,000 would be $2,700. If you compounded yearly, it'd be about $2,600, so about $100 different. This one down here, the green line, this is how much the banks are actually currently paying right now, continuously compounded. Banks are currently giving 0.01%. I just looked it up. And so if you just left your money in the bank, this is what it's doing. After 10 years, you've made $1 on your money, just letting it sit in the bank. So that was after 10 years. Then I went ahead and I looked at it. I said, well, let's look at it in 20 years. Let's see what happens. Does it make a big difference? After 20 years, the continuously would have 7,300, 7,400, while the compounded yearly hasn't even broken 7,000 yet. And if you've let your money sit in the bank, you've made $2 at this point in 20 years. And of course, I wanted to carry this out a little bit further, so I looked at 30 years, just comparing these. Continuously, again, is outpacing compounded yearly. 20,000 now after 30 years versus 17.5. If you've left your money in the bank at this point, you've made $3. And then our last one here, I said 40 years, so when you guys would retire, it got clipped off up here. I believe it is a 54. Something 90. I'd have to regraph this. Sorry about that. So after 40 years, your $1,000 would grow to 54,000 if it's compounded continuously, versus 45,000 if it was only annually. So almost 9,000, 10,000 difference. And if you just left yours in the bank, that $1,000 you got on your 20th birthday or your 16th birthday, you'd have $4 at that point. So this is just a 10% interest. So clearly you want to make a good choice when you guys start to make money. Now, let's go ahead and just use this equation here real quick. You have an account with an annual interest rate of 8%. You have $500 in the account today. How much would you have in 40 years? So it's just A equals, we start with 500, e to the rate 0.08 times t. We're putting it in there for 40 years. And so our work looks like this. 0.08, clear that, 0.08 times 40. So that gets my exponent. Then I'm going to hit the e to the x button, and then I'm going to take it times 500. And so $500 would be worth $12,266 in 40 years. Brenda invests $4,848 in account, 5% compounded continuously, balance after 10 years. So it's the same setup, principal, e to the r times t. Again, calculate your exponent first. 10 times 0.05. Raise e to that power. Take it times 4,848. And you end up with about $7,993.00. John invests money in an account with an annual interest rate of 2.6 compounded continuously. After 15 years, the amount reaches this. What did he start with? So in this case, we don't know. We do know A, the amount he ends with. We don't know the principal. We know our rate. We know our time. To do this now, what we're going to essentially do is just divide this stuff away to get to P. So if we divide both sides by that, and I'm writing it this way so you can see how to do it in your calculator. This is what you'd like to do. All right, now where you round and everything, you just got to be careful with. So let's figure out our exponent first on the e. 0.0263 times 15. We'll raise e to that power. So now we're at 1,912.41, and we'll divide by 1.484. So divided by, there we go, 1.484. And it looks like that's no way right. I'm going to pause here for a second because the bell's about to ring, but something's driving me nuts here. Let me try this again real quick. 0.0263 times 15 equals, raise my e to that power, that's 1.484. 1912.41 divided by 1.484. That's better. Looks like he started with about $1,288.69. And so that's it. Your homework assignments are very, very similar to these. It is another Google form. So all you have to do is go to our classroom, click on the form, and it'll take you right to the assignment. You don't have to turn in work, but you certainly are going to want to write down things so you make sure you enter it correctly and choose the correct answer. So to reiterate today's big thing, oops, as I erase it, it is make sure you know how to use the continuously compounding interest formula.